We're back with another Geek Out episode. Richard Campbell, a developer and podcaster who also dives deep into science and tech topics, is back for our second Geek Out episode. Last time we geeked out about the real science and progress around a moon base. This time it's why is there life on Earth? Where could it be or have been in the solar system and beyond? In case you didn't catch the first Geek Out, episode 253, this one is more of a general science and tech episode. I love digging into the deep internals of all the tools of the Python space, but given all that's going on in the world, I thought it'd be fun to take a step back and just enjoy some fun geekery and give you all something to sit back and let your mind dream. This is Talk Python to Me, episode 276, recorded July 14th, 2020. Welcome to Talk Python to Me, a weekly podcast on Python, the language, the libraries, the ecosystem, and the personalities. This is your host, Michael Kennedy. Follow me on Twitter where I'm at mkennedy. Keep up with the show and listen to past episodes at talkpython.fm, and follow the show on Twitter via @talkpython. This episode is brought to you by Brilliant.org and us. Here's an unexpected question for you. Are you a C# or .NET developer getting into Python? Do you work at a company that used to be a Microsoft shop but is now finding their way over to the Python space? We built a Python course tailor-made for you and your team. It's called Python for the .NET Developer. This 10-hour course takes all the features of C# and .NET that you think you couldn't live without. Entity Framework, Lambda expressions, ASP.NET, and so on, and it teaches you the Python equivalent for each and every one of those. This is definitely the fastest and clearest path from C# to Python. Learn more at talkpython.fm/.net. That's talkpython.fm/.net. Richard, welcome back to Talk Python to Me.
Hey, man, it's great to be back. I'm flattered. You know, I generally don't have a guest back within a year unless something really special happens. So, was it only February the last time I was on?
Yeah, it wasn't that. Let's see. Yeah, February.
So it's only 100 years ago, right?
Well, yeah. February was extremely long ago, and it wasn't that long ago. Like on wall time, it was 5 months.
Yeah,
but in societal time,
the world, everything has changed.
Everything has changed.
Yeah, it's astonishing. This is the longest stretch I've been home in 10 years. Yeah. Maybe longer, yeah. And certainly my wife would be the first one to tell you that.
Adjusting to having you permanently here instead
around
of
all
half the time
by the way,
out somewhere.
Beat down that honey-do list. Like, it's nailed. But she's run out of things to keep me doing, so.
Yeah, our house is looking pretty taken care of as well. Like, what else are you going to do, you know?
And everybody's yard's amazing. It's really something. I'm super fortunate. I live in a great neighborhood where most of my neighbors, at least one day a week, we all go out on our driveways and sip a glass of wine, you know, near sunset and chat a bit. So
yeah, those types of things really are making a big difference for folks. Like, do that as well. Meet up with people, you know, sit outside and have a beer or something. Yeah, that's good.
Something to connect with the broader community. It's funny how valuable that is. You don't think about it till it's a problem, till it's a challenge.
Yeah, well, and you know, being developers, I suspect that we feel less disconnected than others.
Yeah, I think you're right. I work a lot in the IT space, and I realize IT people not only were just busy because there was so much to do, but that, you know, most of your work is crisis to crisis anyway. So this was just another crisis to process. In some ways, I don't think they've actually dealt with the reality of the disruption of society because their job is calling them and they're useful and important at this particular time. But yeah, technology's kind of saved our bacon on this pandemic, I think. Not that we're anywhere near done.
No, we're definitely not done. Definitely not in the U.S. for sure. But yeah, I think we're pretty fortunate on the timing. But yeah, so 5 months ago, not that long ago, but again, quite a different time. So let's maybe start our whole story here by just summarizing what this Geek Out idea is.
Yeah.
Previously, you were on talking about the moon base.
Right.
This was the moon base Geek Out, where we just dove into this concept of a moon base and how people are going to get there, what it might be like, and so on. So we're going to touch on something sort of similar, but not the same for sure this time around. But you've done many, many of these. How many did you say? Like 86 or something?
Yeah, I think we're right at 80 right now. And I have kind of stopped making them at the moment because I'm pouring most of my research energy into the book, into the history of .NET. And it's just, you know, it's way more consuming than I realized. Like, I've been doing more interviews just this week as I'm getting through the body of the work and really getting a narrative assembled, seeing the holes, and then good news, knowing enough people that I say I know who to fill this hole with. So I'm going and knocking down more interviews. So yeah, I've worked on that bloody book for 2 years, and God, I hope I can get it done this year, but it's just been a lot.
That's definitely a big project. And I know last time you were on, we talked about it.
It was killing me then. It still is. Well, and the other thing is I've promised myself that when the book is finally out of my head and out in the world, I will stand the Geekouts up as their own show. That people love the topic. I love the material.
Yeah, I think they deserve to be. I mean, that's 100 hours or so of really interesting, deep research into stuff that most people are not talking about. Definitely not at that level.
I think you're right. And if I have any particular talent, besides being just a good researcher, is that I do adore the complexity of things. I find a lot of science communication is oversimplified for my taste anyway. And so getting into the more complex elements and then being able to service them in a way that's still palatable, that you actually enjoy. Hey, this is why this is hard. What we don't actually understand about these things.
Well, that's a careful balance you got to cover. I mean, I've read a lot of like science for non-scientists books, like Fermi's theorem and other stuff that's been covered, the stuff, the Large Hadron Collider. And, some of those books, they're just dry.
Yeah.
Right? Some of them are like not realistic. They don't actually, you don't really feel like you've learned science on the other side, but there's a few clear ones that are like, do both, and they entertain and they inform, and it's amazing.
Yeah, when you get it right, it's really something. I also think that intersecting sciences too, especially when you talk about a subject as tricky as life in the solar system, it's not just about astrobiology or aerospace engineering. It's also a lot of other aspects of biology and physics that come into play, that it's the composite of that knowledge that really gives you a sense of what's possible in the solar system, much less beyond.
Yeah. And so you do these two podcasts. You do .NET Rocks and you do Run as Radio.
Yes.
And in the .NET Rocks genre, every now and then, when you're not deep in a book authoring, you will go and do research into one of these areas, and you've been calling those Geekouts.
Yeah.
So,
and really what it is I'm always doing the research anyway. Like my idea of a perfect Sunday morning is tearing through a couple of scientific papers in the topic areas that I care about, which are pretty broad-based. And so I was always making notes anyway. It was Carl's idea to start the Geekouts, which goes all the way back to 2011. And really what a Geekout means is me taking a cut of my understanding of a topic at the time and making it into an hour-long conversation. That's in the essence of what it is. So when it comes to Life of Other Planets, I did do a Geekout this in 2018. And so when we talked about doing another show on it, I went and looked at those notes, and I looked at the new stuff that I've been gathering in that area. It's like so much has happened in the past 2 years.
Yeah.
Like it's just astonishing how much the understanding of the way planets operate and the way life can exist in just a couple of years, that it just, for a 2-year-old show, felt stale. Like
it's crazy.
It was at the time when the Cassini had already just been deorbited the fall before. I did that show in 2017. And they're still writing papers off Cassini data. They figure there's 10 to 20 years of more writing off of what they gathered from that spacecraft. And so just those publications alone sort of change the way we think about where life could exist in the solar system.
I think maybe just, understanding what is required for life is a good starting point as well, right? Because for so long we thought, okay, we need liquid water, we need sunshine, the Goldilocks zone you hear talked about a lot, but as we'll see going through it, that's not necessarily the case. One thing I was thinking is, are you surprised that we've not recreated life in a laboratory setting? Well,
and there's an argument as to whether we have or not, because we're getting cleverer about our ability to combine things. I ended up, in prep for this conversation, rereading a couple of Carl Sagan's papers. And Sagan was he also created the Search for Extraterrestrial Life, right? SETI, as well as a whole bunch of other things. But he worked really hard on what would you do to detect life, and what would that even look like, and broaden our understanding of it. So one of the things that came out of an awful lot of that research was that the ingredients for life are pretty much everywhere.
Yeah.
So now it's really about cooking technique. How do you assemble them? What is the perfect mixture? And so that whole idea of the Goldilocks zone is this is the point at which a planetary-sized body orbiting a star can have liquid water on the surface, which was firmly, at the time believed a necessary requirement for life. And so as we've started imaging planets around other stars, and there are different kinds of stars like brown dwarfs, like very dim stars, that Goldilocks zone is tremendously closer to the star, but that has other side effects. Like almost certainly when you have close orbiting bodies like that, the body will end up being tidally locked. So you can imagine the effect that you'd have on the Earth if it was orbiting the star, but one side of the planet faced the star all the time. That is, one side is always lit and one side is always dark. Well, that's going to cause some troubles, right? There's some impacts.
You think about just the tilt that causes winter and summer. It's super minor.
Well, and yet I think incredibly important. It's when you start looking at the different bodies in the solar system, you see that it's only those small variation differences that may be crucial. I would go a step further, and this is like even more recent reading, is that are the continents essential to life? Not that they're land masses, but that they force warm water to circulate away from the equator and up towards the pole. So what we've known as the North Atlantic conveyor is a pump system, essentially, that exists in the ocean where water is warmed in the Gulf of Mexico and then is drawn up the eastern seaboard of the United States all the way to the Arctic, where the ice there drives that water down, cools it, and that creates this pump. And the side effect of that is that the North Atlantic is substantially warmer than it ought to be. And so it provides more rain and more heat to the northern latitudes into Europe, which makes them far more habitable.
Yeah. Europe is super far north, much more than my conception of it relative to other places.
Sure.
And I think that's partly why, right?
And in fact, we have evidence now that in the around 1600s, the conveyor broke down to some degree, and they called it the Little Ice Age, that in Northern Europe, where people were already living, winter got dramatically worse. The canals of Amsterdam froze. So, it makes a big difference. It is part of the dynamics of what makes a habitable world. Where can life evolve and advance? There's a lot of different ingredients in that.
Yeah, absolutely. Well, let's start our exploration of this whole idea with what I think of as the two classic thought problems or thought experiments here. And that would be Fermi's paradox and Drake's equation.
Right. And so Enrico Fermi, father of the atomic bomb, after becoming the destroyer of worlds, and to his credit, then staying in the process to stop humanity from using them successfully, I might add, so far, then came up with that whole, his paradox was, given that astronomy is showing us just how many stars there are and how many galaxies there are, the inevitability that even if a tiny fraction of the planets that exist can carry life, where are they? Because there should be lots of them. It made no sense. And it was Frank Drake that went deeper into that as part of the original SETI gathering, where he started building this probabilistic formula known as Drake's equation that sort of went down to how many stars have we got? What's the rate of new stars being made? How likely are they to have planets? How, are they in the conditions to support life, which is a big factor of this? And then, does life actually evolve? What's the likelihood of that? Does it actually advance intelligence? And then can it communicate in a way we can detect? And then how long that lasts as a society before it either...
Right, before society breaks down and the preppers
they die out
and whatever, right? This portion of Talk Pythonomy is brought to you by Brilliant.org. Brilliant has digestible courses in topics from the basics of scientific thinking all the way up to high-end science like quantum computing. And while quantum computing may sound complicated, Brilliant makes complex learning uncomplicated and fun. It's super easy to get started, and they've got so many science and math courses to choose from. I recently used Brilliant to get into rocket science for an upcoming episode, and it was a blast. The interactive courses are presented in a clean and accessible way, and you could go from knowing nothing about a topic to having a deep understanding. Put your spare time to good use and hugely improve your critical thinking skills. Go to talkpython.fm/brilliant and sign up for free. The first 200 people that use that link get 20% off the premium subscription. That's talkpython.fm/brilliant, or just click the link in the show notes.
Or perhaps evolve away. There's a group of thought that says that the actual purpose of a universe is, like every other composite creature, to make more of itself. And so one of the possibilities is that in the end, a successful universe is one that creates conditions where advanced biological life can form, become intelligent, develop technology that ultimately leads to being able to make their own universes. Which one of the ways you could answer Drake's equation is say the reason we haven't heard from any other life forms is that the window between you developing technology and being able to make your universe is a few thousand years, and then you're gone. You've moved on. Why would you hang out in this universe? You can make your own.
Right. You made your wormhole and you've got the actual perfect place you've designed and all that.
I mean, you could look at it the same way as when you climb out of the cave or you climb out of the ocean. Like, it's just the next logical evolution of an intelligence is to go make universes.
Yeah. And the math of Drake's equation, you think about the math when you do astrophysics and astronomy, relativity, all that stuff is insanely complicated.
We know so much more now. In 1961, when he writes that equation, we did not have a good count of stars and star formation. We certainly do now, right? We know that roughly 3 solar masses worth of stars are formed in our galaxy alone every year. So it might be one big star, it might be a bunch of little ones, but it's a constant thing. We know that virtually every star we've ever looked at that we're able to see reasonably with our exoplanet systems has planets. Planets are super common. Like everything.
That's recent news, right?
Yeah,
like
that's
within
just
10
past few
years or so. This is a certainty, not a speculation.
Right, because we're counting them, we're finding them, we're getting better at finding them. We're even getting better at finding ones in the Goldilocks Zone and likely rocky, roughly 1G worlds. When our first sensors were being used to find exoplanets, we could only find hot Jupiters, stuff that's Jupiter size or bigger, orbiting very close to a star, because our senses weren't that good, right? We weren't able to measure the wobble in stars well enough to sense something small. So we sense something big. So one of the arguments was, there's lots of planets, but they're not good ones. But now, as the sensors have gotten better, we are being able to say that rocky worlds seem to be pretty common too. So every hardening number, every maturing estimate that we've got around Drake's equation points to more, not less, until you get into this life part. What does it really take to support life? And there's where our solar system suddenly is a great example, because we have other planets, some of which, especially when you look at something like Venus, it ought to be life-sustaining. What's gone on there? And again, in the past few years, our knowledge of that has expanded dramatically.
Yeah. Yeah, absolutely. So Drake's equation is this interesting, basically 7 or however many factors ways to speculate, because the math is just independent probability times independent probability.
Right.
Out pops another number. And so let's try to put some concreteness around the speculation, I guess. Let's just look at here. Like, we know there's life on Earth. You and I were talking. We're pretty sure we're not in a simulation.
We're not sure about that at all, but close enough. Probability says that we're almost certainly a simulation.
Yeah, yeah. So let's just, it's a little bit like you started off, right? Like, we think that it was the sun and the liquid water on the surface and all of that turned out to be most important. But then people started going into the ocean and finding volcanic vents, and that kind of broke some stuff.
The Woods Holes finds in the Galapagos is where they first found. They speculate, again, you always have amazing people who can come up with an idea that, hey, look, like there's volcanoes, and above ground volcanoes have vents. Why wouldn't underground volcanoes have vents? In fact, why wouldn't there be vents everywhere? And so then they build a theorem around that and say, well, we should be looking for warm spots in the deep water. And so then they build a sensor array and drag it behind a ship, which they did in the Galapagos, Galapagos is very much like Hawaii in the sense that it's literally just a chain of islands made from volcanoes. And they found evidence of potential vents. It leads in the late 70s to the Alvin submarine going down, and they find clams in the bottom of the ocean. Like, what the heck is going on here? And they follow this trail of clams to a black smoker, to a hydrothermal vent spewing iron sulfides into the water, and the water's 700 degrees Fahrenheit, like screaming hot, and it's surrounded by life. Some of it is like surface life, like clams that have found a new ecological niche, living in the dark, surviving off of the plankton that grows around that vent. Some of it is unique to the area, the tube worms and other strange critters. It's just like here, what should have been nothing, should have been a desert at the bottom of the ocean. There is this wellspring of life in the absolute pitch black, but there is chemical and thermal energy available. And so that sort of changed the math. It just said, hey, as long as I have energy in the form of chemistry and heat and still water may be the undeniable one, the intractable one. You know that science fiction used to speculate around the idea of silicon life. I just read a great paper where it said, we like silicon as potential life because it's just one tier down on the periodic table below carbon. We know we have carbon-based life. We are carbon-based life. And so if you stay in the 14th column and you go down one, you get silicon. And it is also a tenetary atom in the sense that it'll make 4 bonds, just like carbon will, but it doesn't make them anywhere near as well as carbon does. And so it probably doesn't work. And it would need, and they get into this idea of carbon combined with water. And you really need to throw some nitrogen in. They call it CHON, right? Carbon, hydrogen, oxygen, nitrogen. You get those basic elements together. That's all of organic chemistry, more or less.
Yeah, more or less.
And so the water mix might be optional. The good news is every bit of astronomy we've done shows water is everywhere. Water is just, it's not even, and in fact, your amount of available water tells an awful lot about how your planet's doing one way or the other. So water's pretty common. Carbon, pretty common. Like, we're doing all right in those respects. We could probably find life anywhere those things exist.
Right. And we found water in the craters on the moon. We found evidence, at least, of water in Mars.
We're pretty sure there's actually a lot of water on Mars now. We're just being a little careful going too near it because there's almost certainly life in it. And we don't want to accidentally destroy it.
Yeah, that'll be amazing. You've got Venus, which has evidence of something flowing a lot on it. If you look at the shape of the ground.
Yeah, the Venus Express mission, which is still in orbit today, but it did a lot of the detailed modern mapping of Venus. So it definitely shows ocean bases and things like that. It also shows over 100 large-scale active volcanoes scattered around the planet. So, and by large, they mean like big Hawaiian island large, right? Mauna Loa, Mauna Kea, but 100 of them. Like, okay, so there's a reason why there's a lot of sulfuric acid in the atmosphere of Venus.
Right.
But one of the things that they really dug into from there is they said, well, look, seeing that the ingredients are so common, but clearly Venus isn't like that anymore, right? Like, the surface of Venus is 90 times atmospheric pressure. It's 900 degrees Fahrenheit there. Lead will melt on the spot. The toughest Soviet lander ever made, Venera 11, lasted 2 hours on the surface before it broke down. Like, it's not fun down there, but it doesn't look like it was always like that. That a billion years ago or so, Venus was a water world, that it had oceans. But something went wrong.
Yeah.
And the went wrong seems to be the magnetic field. The magnetic field of Venus was not strong enough to repel solar wind. And in the end, solar wind's nothing magical. It's the byproduct of fusion of the sun, spews a constant stream of highly charged protons from the star all the time. And it hits everything all the time. And because it's highly charged, it's magnetically sensitive. So our very strong magnetic field on the Earth pushes those protons away. It actually, if they're low enough energy, it'll capture them in the Van Allen belts. But the main part is that it doesn't get to the atmosphere. Because when a high energy hydrogen atom shows up like that, it finds itself another hydrogen atom. They like to be in pairs. And so it'll rip a hydrogen atom out of the atmosphere in a big old hurry. The typical place it's going to get it from is a water molecule. So it'll yank a hydrogen out. One of those high energy solar particles is going to grab a hydrogen atom off of a water molecule and head off into space. And then you'll end up with a hydroxyl radical, an OH, which is then going to try and combine with something else, or maybe that other hydrogen will get ripped off as well. And then you have elemental oxygen. And elemental oxygen does not like being elemental. It finds a home.
Yep.
And so it grabs whatever it can find. And in the case of Venus, it grabbed carbon atoms. and turned Venus. Venus gradually lost more and more of its hydrogen, and all of that oxygen found home in carbon, and you had a ton of carbon dioxide until you get the atmosphere of Venus that you have now.
Which is incredibly dense, as you said.
Yeah.
90 times, even though the size of Venus, the gravity of Venus is about the same. It's not
Pretty
like
close.
Jupiter or something, say.
No.
But yeah, it's just turned into this hot, dry place.
Yeah, but gravity is not the thing that protects an atmosphere, it appears. It's the magnetic field that makes the difference. And pretty much the same thing has happened at Mars. It's just that Mars is further away and it's smaller. Right? It's only half the size of Earth, right? We always think of Mars as close to Earth. Venus is way more related to Earth than Mars is. But Mars, too, was once a wet world. Our detailed maps from the Mars Odyssey and other mapping satellites has shown us where oceans ran. And in fact, still seeing occasional bursts of water come up, bubble up onto the surface and roll down hillsides and then disappear again because of sublimation, because the atmospheric pressure is so low. But same thing happened. The hydrogen got stripped away. The oxygen found a home. It made a carbon dioxide atmosphere, granted a very weak one. It's also why the planet's red, because it bombed with all of the iron it could find and turned the planet red. But in both cases, it's the weak magnetic field that has been the big difference maker for that planet.
People mostly think of Mars as like the old Earth or whatever, right? Long ago, it might have been like that because Venus is so different with its temperature. But
yeah, but they're both the same result. If you make a heavy-duty dense carbon dioxide atmosphere, you get a runaway greenhouse effect. If you don't have enough mass to hold on to your atmosphere well when the atmospheric stripping comes, you get a dry desert like Mars.
Yeah.
But they were both likely wet worlds and quite possibly had life on them. Whether or not any of that has survived now seems unlikely, but NASA's been admitting that they want to be really, really careful around any native life on Mars. And their protocols for putting stuff down on the surface of Mars to detect life are strict enough that they generally don't want to build spacecraft that way because they need to sterilize the spacecraft so thoroughly that it's actually hard to make a spacecraft. In order to really sterilize it, to kill bacteria that will survive the journey in space to Mars and re-entry, you have to bake the spacecraft at incredibly high temperatures. And most spacecraft don't survive the baking process. So far with the missions they've been sending to Mars, they stay away from areas that are likely to have life so that they don't have to follow those steeper protocols.
Right. And how certain are you that a little tiny bit didn't get through, right?
Yeah.
It's microbiology.
Constant concern. Well, and a great example of this is the Israeli Mars lander had tardigrades on it. The lander was supposed to do an experiment with tardigrades, which they often called water bears. There's these little microscopic critters that are insanely tolerant to harsh conditions, insanely tolerant to being dried out and being wetted and brought back to life again, to hard radiation conditions and so forth. So tardigrades are great, interesting things to experiment with. Well, the Bear Sheet lander didn't make it to the moon. It hit the moon just with a little bit too much vigor. Yeah, you can see a lunar reconnaissance orbiter picture of where it landed. It's a big old splat. But there's also a conversation that says this tardigrades probably survived. We have contaminated the moon with water bears.
In that little tiny spot. That's
in
right.
that spot. Yeah. Now I don't think they're going to rise up and repel, and attack us someday, but it speaks to the reality that when you get down to microscopic life, they're incredibly resilient, and our risk of contamination is really significant. And this gets into this really interesting ethical discussion around
how do you look for life if it's almost
the
like
process of looking destroys it.
It's like if you observe it, you may change it.
Yeah.
So you got like one shot to check. Is life here?
Yeah, and how you check it. And then you want to study it over time, right? And so the more we've learned about Mars, the more we've come to appreciate that there's very likely briny liquid water under the surface. One thing we have not done much of in all of our explorations of Venus and Mars and the moon and so forth is really dug into the ground at all. And so you don't know what's going on a few feet down. The Earth itself, depending on where you dig, transforms amazingly as you dig down. The first meter is one thing. The next 10 meters, something else. 100 is something else again. The first kilometer again, and so forth on down. We just don't know for sure. But as the models have gotten more coherent and reliable, it looks like There's briny, liquid, salty water, subsurface of Mars, and it almost certainly has bacterial scale life in it.
Yeah.
And because the question is it worth constructing a mission to do that, to actually test for that safely, which is very challenging to do, to teach you exactly what, other than to assert for sure there's bacterial life on Mars.
Right. And that would be interesting, but how significant is it?
Very true.
It would be much more interesting to find creatures that move around in some way, right? And so that brings us back to, well, if it's actually the magnetic field that matters, other places around here have magnetic fields as well, right?
Well, and part of what led us to that understanding were the Galileo and Cassini missions out to Jupiter and to Saturn, respectively, because there you've got an epic magnetic field. It's just not the moon's field. It's this gas giant's field, and there's no solar radiation getting that. In fact, you get more radiation off of the host planet than you do from the sun once you get it to that
Saturn
scale.
has crazy radiation, right?
Yeah, and so does Jupiter, and pretty much for the same reason. Is you compress gas to that point, like they talk about metallic hydrogen and things being down there, you create these electromagnetic fields from the friction of everything moving around that they're incredibly destructive. They certainly will kill any human that gets anywhere near it, but making electronics that tolerate that, you wonder why these space missions are so expensive. It's really tough to make hardware that can tolerate the radiation exposure that they get. And they don't orbit in neat, tidy orbits the way you think about it from science fiction. And both Galileo and Cassini did orbits where they got a long way away from the gas giant on a regular basis to decrease their radiation load as well. It helped them also do maneuvers. When you're at that far apogee, when you're further away, it takes very little fuel to tweak your orbit and be able to make a close pass on a different moon. But it means that you have shorter bursts of time at higher speed in those strong radiation belts.
Right. You whip by them really quick, take your measurement, and get out.
But, speaking of detecting life, the Galileo mission, which flew back in 1989 out of a space shuttle back when A, space shuttles operated, and B, they were still launching satellites, which they stopped doing because it finally clued into someone after that how dangerous it was to put a rocket engine inside of a space shuttle full of fuel when you're going up. But what was cool about, many things were cool about the Galileo mission. Its mission to Jupiter was great, but part of the way that it got to Jupiter is it actually did a slingshot maneuver off of Venus, and then another one off of the Earth on its way out, which took it about 6 years. But it was Sagan, remember him, Carl Sagan, who said, hey, can we craft an experiment for Galileo to detect life on Earth? Like, given this limited set of sensors that we're going to send to Jupiter to go look at the moons and go to Europa and all those cool things, like, what would we do to actually detect life on Earth? And so he was primarily using spectrographs. So he's imaging the atmosphere to read it and saying, what are the unique signatures in Earth's atmosphere that are life indicators? One of the points he made in this paper from 93 was that there's atomic oxygen in the atmosphere. Because oxygen doesn't like being on its own, it always is going to find something to combine with. The only way you would measure atomic oxygen in the atmosphere is something is producing it constantly. And his argument was that is almost inevitably life. Like he really can't think of another model that is constantly producing oxygen. In our case, it's plants, right? Plant life rose first in the form of algae on the Earth, and it's what pumped oxygen into our atmosphere that created all these possibilities, right? Our ambient atmosphere was mostly nitrogen before that. It wasn't until plant life really got going that we started having ambient oxygen. But he also indicated that methane was an interesting indicator as well, in combination with oxygen. Methane is super simple. It's a carbon and 4 hydrogen atoms. It is created in space all the time. Right, cosmic gases form into methane, regularly, and if you got lots of methane, it's probably created that way. But methane does not exist in amongst atomic oxygen very easily. So where it does exist, it means there's some kind of what they call methagenesis going on, or some process is making methane, and it's probably life. And so, the most famous methane producer on the planet for most people are cows,
right?
Because they ferment their cud, their grass, and a byproduct of that is methane, which they mostly burp out, not the other way. But it is an interesting indicator. That mixture of atomic oxygen and methane is probably a really good measure of life. And the delicious part of this, and it's one of the reasons I bring it up in this story, is so he writes that in 93, makes that postulation, and years later would find that exact mixture elsewhere. And we'll talk about that when we get there.
Yeah, for sure.
And it's interesting, the Galileo mission was focused on Europa, which is an icy moon in orbit around Jupiter.
Yeah, and we have all these moons around Jupiter, right? And Saturn. I don't remember which, but it's like 20 to 80.
Yeah, I think you're over 80 for Saturn alone now, because when you start sending spacecraft close enough to actually orbit, the Voyager missions were just flybys. They whizzed by Jupiter and Saturn. They saw a few things, but when Galileo orbited around Jupiter for years, and so found a lot of moons, as opposed to the ones that Galilei saw from a primitive telescope. He saw the first 4. Right.
Yeah, but isn't it supposed to be cold out there?
It is very cold. There's no two ways about it, and that was the expectation, right? Is that we're going to go see ice balls, and then when they actually imaged Europa, they found there were cracks in the ice. I mean, that makes no sense, right? Like, why would there be cracks in the ice? And not only that, but wherever there was cracks, there was red, sort of a muddy red-brown. Well, here comes Sagan again. They were trying to figure out what it was, and they had this theory that it was a chemical compound, and so they started making it on Earth. So take your common cosmic gases, the stuff that naturally forms, like methane and ethane, ammonia, hydrogen sulfide, those kinds of compounds, all relatively simple compounds. Carbon with a bit of hydrogen, nitrogen with a bit of hydrogen, that sort of thing. And then expose it to ultraviolet light and a few cosmic rays. And it changes. It changes into a weird reddish substance that is actually really tough to measure. For a long time, they called it star tar, which is a good name.
Okay, yeah.
But ultimately settled on tholene, which is derived from the Greek word for muddy, because it is kind of a sticky, muddy substance. And so the theory goes that you have these common compounds, and then they come to the surface and get irradiated. And then that irradiation turns it into these sort of primitive compounds. And since Europa was really the first time we saw tholines in substantial amounts all along the cracks in Europa's ice. And we've seen them elsewhere since then. So the model for what made Europa interesting then was this combination of a very strong magnetic field from Jupiter, also very strong tidal fluxing, so that the gravitational pull of Jupiter is so strong it flexes Europa regularly, which keeps the core of Europa warm. And so the estimates now is that there's 100-kilometer deep liquid ocean underneath the ice of Europa.
Talk Python to Me is partially supported by our training courses. How does your team keep their Python skills sharp? How do you make sure new hires get started fast and learn the Pythonic way? If the answer is a series of boring videos that don't inspire, or a subscription service you pay way too much for and use way too little, listen up. At Talk Python Training, we have enterprise tiers for all of our courses. Get just the one course you need for your team with full reporting and monitoring. Or ditch that unused subscription for our course bundles, which include all the courses, and you pay about the same price as a subscription. Once. For details, visit training.talkpython.fm/business or just email sales@talkpython.fm. And that flexing has got to be causing some volcanic-like behaviors.
Yeah. They call cryovolcanoes, right? That you get these bursts of warm water, above freezing water, that bubbles onto the surface, carrying these simple compounds, your methanes and ethanes and ammonia and so forth, onto the surface, where it gets irradiated by the sun and turns into tholins.
Yeah.
And I would point out that Arthur C. Clarke, who to this day I am still convinced is actually a time traveler and didn't die, but rather went home, who predicted geostationary satellites 20 years before anybody could fly them, also wrote in the book 2010, his sequel to 2001: A Space Odyssey, that, the star people said, all these worlds are yours, save Europa, attempt no landing there. And the first time we get a good look at Europa, it looks like there's something there.
Yeah, that's insane. That was such a great imaginative story. And wow, I didn't realize that part.
Oh, I remember when the paper, when the stuff came, the reports came out, I looked at it, I was like, how did he know? He keeps being right. It's crazy.
Yeah, that is totally crazy. It's totally crazy. Yeah, I would love to see us go there, even with that warning, maybe. I don't know. I mean, the problem is once you go there, the clock is ticking for at least very small microbiology.
Well, there are mission proposals like this thing called Jupiter Express where they want to put a lander down on the ice close to one of those cracks. They want to melt their way through the ice and drop a submarine down.
Yeah.
And motor around in that
a nuclear
ocean.
Space heater.
You guess what you're going to need, right? A radiothermal generator, which is generally what they use out there anyway, because there's not enough sunlight to really make solar work. And most of those RTGs generate 4-to-1 heat to electricity. So, your typical RTG, like the one that's on the Curiosity rover on Mars, is generating 100 watts of electricity and 400 watts of heat. So you could get a big one and put it down on that ice, and it's not only making electricity, so it's still able to communicate to the surface, but it's also generating enough heat that instead of you trying to dissipate it, you're actually pumping it into the ice to melt your way through it.
Yeah.
And now you get into the question, like, knowing what we know now, that there's almost certainly liquid water down there, and it's caused by these tidal effects, which means there's cracks in that core. If it's warm enough, maybe there's hydrothermal vents down there. And knowing what we find in our hydrothermal vents, what would we find in their hydrothermal vents?
Yeah. It's exciting. It's absolutely exciting. Mm-hmm. And another place that's in this kind of realm is Saturn and its moons.
Mm-hmm. So, the Galileo mission was the late 80s, early 90s. Cassini was one of the last of what they called the great observatories. They built these huge spacecraft. They don't build them this big anymore. Cassini was a tank, arguably one of the largest Explorer spacecraft ever built. It's literally the size and weight of a large school bus, of a full-size bus, right? Almost 6 metric tons.
Wow. That's like 3 cars.
Yeah, a huge machine. Yeah. And left in the late 90s, got to Saturn in 2004, operated for 13 years. It was originally planned for a 3-year mission, but they kept extending it. And in fact, they intentionally deorbited it because what they found in the moon system of Saturn was so profound that they weren't willing to take a chance that Cassini might accidentally crash into one of the moons when they lost control of it when it ran out of fuel. And so instead, they intentionally deorbited it into Saturn's atmosphere. And it sent data right up until it lost control. It hit enough of the atmosphere that it started to spin. But the story of Saturn's, the exploration, of course, the big one was to see Titan. And Titan is the largest moon in the solar system. In fact, Titan is larger than Mercury. It'd be a planet, except that it happens to be orbiting a gas giant. And the Voyager missions had imaged it well enough that they knew it was completely clouded over, incredibly dense atmosphere on it. And so they had a lander on the Cassini mission called the Huygens probe to land on the surface of Titan. And what it found, there's a great video they composed of all of the photographs of the Huygens probe as it descended by parachute down to the surface. It looks like a wet world. The problem is it is extraordinarily cold. Right? It's negative 209 degrees Fahrenheit on the surface. So bring a jacket, right? It's cold. And so the atmosphere is almost entirely nitrogen with traces of ethane and methane. And in fact, there's ethane and methane clouds that rain onto the surface and cause erosion. And there are lakes, bodies of liquid on the surface of Titan. It's just they happen to be liquid methane. Oxygen, It's cold enough that oxygen is frozen solid there. So you would be able to mine oxygen if you get there. And the atmosphere, the pressure on the surface there is about 10 times sea level pressure, 10 bar.
Is the atmosphere thicker?
It's very thick. And again, it's a decent size. It's not a huge thing, but it's big enough. But so your gravity's low enough and your atmosphere's thick enough that if you could get a warm enough coat and a respirator so you could breathe, you could probably strap a couple of wings onto your arms and fly. Just flap. It'd be enough. You've got enough atmosphere to push against and a low enough gravity, you could probably fly around Titan.
Wow, that would be insane. It's like kind of like swimming, but in the whole sky.
The problem is that at that level of cold, everything is brittle and hard, and it would be very challenging to function there. But it is, if you were picking candidates for places that humans could live, that's one of them. We just have to solve certain challenge, non-trivial problems. but the atmosphere is thick. Is there life there? It's awfully cold. The water, there is absolutely water ice, but it will be like rock. So intensely hard.
Yeah. So maybe not. Who knows?
But that was their plan for Cassini was obviously to drop the Huygens probe on Titan, because this amazing moon. But they were generally going to image all the moons. They wanted to find some Europa and so forth. And it was Enceladus that stole the show.
Yeah, absolutely.
Enceladus is the 6th largest moon of Saturn. So it wasn't high on the rank. They expected it. Well, the only thing that was interesting about Enceladus going in with Cassini was it had the highest albedo of any moon. So it was incredibly white, very reflective. So it was expected that it was incredibly white because it was an ice ball. It was just covered in ice, and so it reflected a lot of light. And so after a few orbits in from the initial mission, one of those orbits was going to get close enough to Enceladus that almost as an afterthought, it's like, we should snap a couple of pictures of Enceladus. Like, they weren't planning on doing anything substantial with Enceladus. And then one of those pictures, when they got it back, there was a cryo geyser erupting on the southern half of Enceladus, and it was visible in the photograph.
Right. They were somehow between the sun and then Enceladus and then the spaceship, right? So they caught it in the light. They
could see the cryo, and again, totally unexpected. And to NASA's credit, they rewrote the mission at that point. They just redid it. Okay, that's now an important body. Let's figure out how we do more passes on it. It's active now. We need to see this thing now. And so while they still mapped a tremendous number of moons for Saturn, and it's over 80 now, and they got pictures of all the other bodies and some great, and learned more about the rings, that figured out that there's a cloud formation on the north and south poles, that it's hexagonal. Like, they learned astonishing things about Saturn.
Yeah.
But they really studied the heck out of Enceladus, to the point where they decided, as they were getting towards the most extended parts of Cassini's mission, they were going to take a chance. And they made a pass past the south pole of Enceladus within 12 kilometers, and ended up flying through a geyser plume. And to the point where the spacecraft almost lost control and spun out. They genuinely, that thing got splattered with that cryo geyser. They took an incredible chance with this machine.
They hit like a hose type of thing at 20,000 miles an hour or something, right? I mean, that's crazy.
You know when you're bombing down the highway and the guy in front of you washes his windshields and it lands on yours? That. In a $1 billion, 6 metric ton spacecraft, 120 million kilometers away from a pit stop. But the byproduct is that they caught some of that material and they measured it. And you know what they found? What? Atomic hydrogen and methane.
Oh, how interesting.
It's the same stuff that we'd measured with the Galileo spacecraft, like in the right ratios, where it's like something biological could have made this. And that is just, from what they thought was an icy ball that wasn't interesting, to we have measured unstable compounds in the effluent of this moon that indicate something down there is producing it.
And lots of water, right?
Well, there's certainly plenty of water, and briny water, salty water, and a bunch of other hydroxyls, other light compounds, again, unstable compounds. But that experiment that Sagan had done 20 years before with the Galileo spacecraft, and that piece of research just sort of mapped neatly onto the data set they got back from Cassini's fly-through of the Enceladus cryovolcano, cryo geyser. And it just, you sit back in your seat and go, what have we found? Look, what do we know now? And of course, there's tholins all over Enceladus.
To me, this looks like our best hope, honestly. If you could go down in the water and find creatures in the water, this looks like a good option to go down and check out.
Yeah, I mean, it's a long way to go, but it definitely worth doing another concept around a melting mission rather than Europa to do it to Enceladus. It's a little bit further out because you're going out to Saturn. It's a smaller ball, and it's certainly active, right? So, one of the challenges you have here is, like, we can see all of the evidence of potential life on Mars, but it's traces from the past. There may still be some hanging on in a subsurface sea, but this is way more active. It's just a long way away.
Right. What you would find in Mars is probably just biological, as you already said, right? Whereas this, mean, there could be something like a whale down there. Who knows?
I would hope for like a barnacle, dude, right? An idea of a filter feeder that means an ecosystem exists where there's microscopic life that eats other really small life that ultimately gets to a filter. Like, that would be astonishing. The most, the higher probability is a slime mold, but, okay, life. But what's interesting is seeing that this theme happens over and over again, that when you have a combination of a strong magnetic field that protects the atmosphere from solar stripping, and you have some heat in the form of tidal forces or core heating, and you have liquid water also generated by those things, you have these elements come together again that show the precursors to life, or the evidence of relatively simple life.
Yeah. Well, really quickly, I know you guys had Rob Connery on your show.
Yeah.
And he had written an interesting book called The Curious Moon, which is like a Learn Postgres, the database.
Yes, but his sample data was NASA's Enceladus data. And what's lovely about that is not only is it super real and so forth, and it's a fun book, and I actually helped him edit it. I was one of the early readers on it as well, and we argued vociferously about it. And it is really a good teaching tool. But, NASA publishes absolutely everything they gather. It's part of their basic policies. And so included in that data is the fact that they actually changed the data structure halfway through the research. When they went to the second phase of, they're like, I don't like this data format. We're going to ship this data format. So you have all those problems. And, Rob is a friend, and I think his book is brilliant, and we all should own it. If you want anyone who wants to learn Postgres, like, there's no nicer way. And you'll work, and the story he tells is a fictionalized story based on real data is delightful, like just really a fun thing.
But that's cool. I definitely want to check it out.
Yeah, I totally encourage you.
So what we've covered so far was on my radar. These are things that I at least knew about. I knew about the geyser. You look at Venus, and it obviously has what looks like Grand Canyon type of structures in it and whatnot. But it turns out if you look farther, there's still interesting stuff out there that was not on my radar.
Well, and I'll skip over the other two gas giants, Neptune and Uranus, for no other reason than we just don't have good data. We've never had a Cassini-class mission out there. There's a big pitch right now to send a major mission to Neptune. It would still take a decade plus to get there. But we happen to be recording this almost right on the 5-year anniversary of New Horizons getting to Pluto. And, New Horizons was a very unusual mission. Pluto is a weird orbit. It was only discovered in 1930. It does not orbit on the ecliptical plane of all the other planets. It's tilted. It also crosses into Neptune's orbit and then passes back out. And in fact, when they were proposing the New Horizons mission, what they were saying was like, listen, we're at a point right now where we can get a couple of good gravity slingshots and get something there in a reasonable length of time, right? In 10 years or so. And if we don't do it now, we won't be able to for like 50 years.
Wow.
And so they got the
crazy
budget. And it was quite a small spacecraft. It's about the size of a piano. And I mean, like a baby grand piano. And it's actually triangular shaped. And it was actually the fastest moving vehicle we ever made. It did a direct ascent to Earth escape. Like generally you put something in orbit around the Earth before you fire another engine and fly it off to Mars or Jupiter or anything like that. They did not do that with New Horizons. It was an Atlas V. It was overpowered, and it just shot as fast as it could to do a slingshot off of Jupiter to get to Pluto, and it got there in 2015. I mean, Pluto at that point was considered a dwarf planet, and it was supposed to be an ice ball. It's out in the middle of nowhere. And the first photos that came back from New Horizons, there was a heart-shaped patch of red, huge, on the side of Pluto. It's all tholins.
Oh, wow. And it's this muddy stuff that you talked about.
Yeah. It doesn't cover the whole thing. I mean, it's very cold on Pluto. Make no mistake, right? It's a very chilly place. Water ice is like rock. There are glaciers of methane and liquid and nitrogen. It may even snow nitrogen there at times because it does have this oscillation in its orbit that it gets closer to the sun when it's inside the orbit of Neptune and then gets colder as it moves further away. But it had more texture and structure, young structures on it, maybe less than 100 million years old, that indicated activity, a trans-Neptunian object, like something so far, far away. And so again, it just sort of shook us up to this idea that the ingredients for life tend to exist anywhere enough of it can gather to coalesce into a structure. After it made the flyby of Pluto, because it was moving awfully fast, it was only close to Pluto for a few days, they were able to do some tweaks of maneuvering to make a flyby of one other trans-Neptunian object, which they've subsequently named Ultima Thule, which is actually two rocks sort of sticking together, but it looks like it's entirely covered in tholins.
Oh, wow.
The whole thing is red.
Oh, wow. How cool.
Yeah. So, the byproduct of this is just this repeated sort of indication that these things keep happening. The chemistry is always there, which brings up the answer to your question, which is why are there no tholins on Earth? I mean, you'd think, other than the tholins we've made ourselves, and the main reason is elemental oxygen. As soon as you introduce elemental oxygen, it is going to rip apart all those tholin compounds.
All right. It just wants to react straight away, huh?
Oxygen is greedy, right? Oxygen always finds a way to grab, you mix oxygen in with ammonia and you get nitrogen monoxide and water, right? Oxygen always gets in there. So I think what we see in these tholins are these early stages of life. And then as it advances, they get destroyed to become resources as active oxygen is introduced to the system.
Right. Wow. So there's a lot of possibilities, a lot of places where this could be. A lot of it is not obvious. It's underground or it's something, but especially those moons sound really, really interesting to me.
Yeah. And definitely a lot of energy around, can we make another mission to Enceladus and land on Enceladus?
Yeah.
And maybe not actually bore through the ice the first try. The chances, I know they're doing experiments now in places like Antarctica to see, can we actually melt through the ice kilometers? Because we don't have good enough measurements right now. Maybe we start with an orbiter. The problem is the flight times are a decade. Like you pretty much commit to a lifetime. So it takes you 5 to 10 years to build a mission, 10 years to get there, and 10 years to operate it. That's a career.
Yeah, that's just insane, the timescales he's work on. And I think we'll probably be coming back to that in a second here. But I think one of the things that's happening recently that's pretty interesting is, what do we do if we want to have people go to other places? Right? So what we talked about so far is, is there life around, black smokers or some other potential thing? Or was there previously life on Venus? But there's some really wild ideas, like maybe we could live on Venus, even though it's 90 times atmospheric pressure and it's 900 degrees and whatnot.
So there's a spot on Venus that is almost 1G and it's 1 atmosphere of pressure. And it's 50 kilometers off the surface. So it's for the most part, above the sulfuric acid clouds, which is good, although we can make sulfuric acid repellent materials. It has a ton of solar power, about 40% more than Earth. And its atmosphere is so dense that you could put a balloon filled with nitrox, with breathable air in there, big enough that you could build a town in it. And it would simply it would float on the atmosphere at that altitude. So cover the top of it in solar panels. Since it's at 1 atmosphere of pressure, if you get a hole in it, it's not like the air rushes out. In fact, you probably make your sphere just slightly higher pressure, so you tend not to have the carbon dioxide come in, but you had the atmosphere come out, but you could easily stitch it back up again.
Yeah.
There was a concept mission developed called HAVOC, the High Altitude Venus Operational Concept, using essentially blimps and rockets to go and explore at that altitude around Venus. But one of the most interesting realizations was that the atmosphere composition at that level has lots of carbon and oxygen and even some hydrogen still. There's still some water vapor at that level, lots of nitrogen, sulfur, and it's all in gaseous form. So if you want to live off the land, if you want to do in situ resource utilization, you just need a gas pump. You just pump the gases from the atmosphere in. And then typically what you do is you chill it, because each one of those compounds turns to a liquid at different temperatures. So you literally are doing cryofractionation, and you separate out each of the fluids into the respective elements, and then you use them in chemistry. You want to make breathable air? No problem, right? You need to make some carbon structures? Yeah, we got those. No problem. Like all of the compounds you need to take care of a lot of your consumables, they're there. It's just that you're building a cloud city, which is weird. Like that's straight science fiction stuff until you understand how dense.
That is straight out of science fiction.
Yeah. Except the atmosphere is so dense. You don't have a buoyancy component. Your breathable air is buoyant. And it's the only place where you'd be able to go outside without a pressure suit. Now, you'd still be wearing something because there's droplets of sulfuric acid, but it turns out Teflon repels sulfuric acid just fine. So imagine wearing a bodysuit, Teflon coated, helmet on, you've got a respirator, but you're not under any pressure. You're not inside a balloon like you are in a spacesuit, so you can move very freely. It's going to be very bright. You have enough radiation protection because there's enough magnetic field and there's enough atmosphere to protect you there. So it's unique outside of the Earth. 1G, 1 bar of pressure, sufficient radiation protection, ton of solar power.
And some resources.
Yeah. And eventually you could build out the infrastructure to have enough resources to at least keep yourself in water and air.
Yeah.
It's more compelling than it ought to be.
That is such an insane idea, but it sounds actually better than living on the moon or living on Mars.
Well, because the moon's always going to be almost, and I mean, not quite a camping trip, but definitely an outpost. It's always going to need supplies.
Yeah.
But, and Elon's keen to get to Mars because with Mars, everybody can relate to Mars. You can see its surface. It sort of has an environment to it. We've made movies about it. But the radiation protection on Mars is simply not adequate. So, all of those cartoony, science fiction-y, we're going to build a city on Mars is not likely. We'll more likely build underground. There has been enough volcanic activity over the millennia on Mars that there are significant lava tubes, so the pre-formed tunnels that you can put a pressurized habitat into. You're always going to have to wear a pressure suit. The atmosphere is simply not strong enough. It's less than 1%. So you're going to have all of the spacesuit problems, which are not trivial. When you get in that low pressure environment, you have huge electrostatic problems. You have the perchlorates, which are an iodine compound that we find in very deserty areas on the Earth as well. The Atacama Desert in Peru has perchlorates, but perchlorates are everywhere on Mars, and they're quite bad for humans. They're quite a nasty contaminant. They have to be chemically processed out, which is not energy cheap.
Right. Energy's expensive out there. You're far from the sun.
Yeah. Solar panels are not great there. We make them work on golf cart sized machines, but as soon as you get any bigger than that, like the Curiosity rover is about the size of a Mini, and it just couldn't be solar powered. The solar cell panels would be too large. So it has an RTG, a radiothermal generator on it. If we're actually going to put humans on Mars, we're going to need nuclear power of some form. And there's a bunch of interesting technologies around that'll make it feasible. But the amount of solar required, the dust problems and the electrostatic problems, it's just not efficient. It's even hard to make solar work on the moon for the same reason. And you get a lot more solar power on the moon than you do on Mars. But you're still talking less than a kilowatt per square meter on the moon. And you're talking half that on Mars and maintenance. It's just not enough power. So, although you get double at Venus, so you have more options there, and you don't have the atmospheric problems. You're still going to need to do some maintenance because they're going to have to resist sulfuric acid and things like that. But it certainly has more possibility. Heat will be a challenge. But none of these planets is going to be...
If Elon built it, if he built his Starship, would you go? Would you take a trip?
Oh, yeah. But I'd want to come back. Yeah. I'll take a ride for sure. I don't have the money for the current generation of space explorers, but the side effect of when Starship works, it's not going to be the trip to Mars. It's going to be interesting. It's going to be orbital hotels.
Yeah, because
they suddenly get way more feasible. Now it's like I could buy a house or spend a week or two in orbit, and that's I'd be tempted. Got a house. Raised my kids. I'm happy to spend their inheritance at this point.
Would be like a really different cruise.
Yeah, really extraordinary cruise. Right? Very, very expensive. But, this may well be coming in our lifetime. Especially, Starship is going to take longer than Elon plans, but then everything Elon plans take longer than Elon plans. But his design seems essentially sound. And if he has 100% reusable spacecraft so that we're only paying for fuel... Now we're talking pennies a kilo into orbit instead of hundreds of... he's gotten... Even Falcon 9 is below $2,000 a kilo to orbit, which is astonishing. Like, it's a revelation. It is literally an order of magnitude improvement.
Yeah.
But Starship would be 3 more orders of magnitude. Like, now 20 cents a kilo? Like that.
That is insane.
You're in the ballpark.
If anyone's going to do it, that guy's going to do it. He's got
don't count Bezos out. The only reason, Elon is a showman for a reason. He needs money. Now, he's mostly showing off to his billionaire friends, right? It's Sergey and Larry that are funding him a lot of the time. But Jeff doesn't need the money, which is why he sort of keeps it to himself.
Yeah.
I think we may get surprised by him that New Glenn is further along than we realize. And that is one heck of a rocket design. And it'll obviously be different than what's known because he keeps himself close to the chest. But his mission is not to put humans on Mars. He's much more in the O'Neill cylinder category. He'd like to build learn how to mine asteroids, build structures in space, and build 1G habitats. Gravity wells are dumb. Like, why would you go back down into a gravity well and make it expensive to get flying around when I can hollow out an asteroid, put some artificial light in the center of it, spin it up so that you have 1G, and fill it full of people and wildlife and resources. And anytime you want to go back into space, you take an elevator to the center where there's no gravity again, and out to a non-rotating rim where you can hop in a spacecraft and take off. Now, that's a tremendous amount of technology. That's probably decades worth of work. But it starts with being able to get into orbit cheaply.
Yeah, absolutely it does. How interesting. All right, let's wrap this up. We're getting short on time.
Sure.
Bring it back to the beginning. So we talked about Drake's equation, which puts a bunch of probabilities together. Almost any non-zero number you put in there, knowing how many stars are in a galaxy and how many galaxies there are,
right,
shoots out a tremendous number of potential habitable places with life forms. And yet there's Fermi's paradox.
Yeah. Where are they?
I mean, we're finding all these exoplanets. What do you think? What is your gut feeling here?
I think that the ingredients for life are super common, but the ingredients for life are super common, but the conditions are more challenging. How do we get a planet with a strong magnetic field so it has an oversized moon? These days we talk more and more about the chemistry of the moon's lower core, that it's not just the nickel iron that's compressed in the center, but also that there are tendrils of spirals of sulfur coming out of them that help amplify that magnetic field. So it may be that there's only particular windows of time in the evolution of a planet where it actually makes a magnetic field strong enough to really defend its atmosphere. And hopefully it has enough atmosphere to defend at that point. But then also is cooled down enough that the floating pieces of land that create land masses don't float so freely that they're just one big land mass so that you have a homogeneous life on it, but rather start to stick to each other and break apart and create plate tectonics that then
create these currents that level out the atmospheric and weather patterns and all that, right?
But also create conditions for rapid evolution. What happens when you fragment the landmass up is you create micro environments for evolution. We wouldn't have kangaroos and all of those weird monotremes if not for the isolation that is Australia. And so how do you create conditions where different things can evolve and then encounter themselves later? And I think continental drift is an important part of it. So you need a planet that is hot enough and energetic enough that it's making a strong enough magnetic field, but cool enough that its plate tectonics exist and are fracturing land to create that petri dish of evolution. Like now you're starting to get into tougher numbers.
Yeah, it's getting smaller.
And then throw into that little indicator I threw in at the beginning, which is when you finally evolve a tool building life that starts developing technology and they go up that hockey stick of technological advancement, how long before they wink out of existence as far as we're concerned, either by destroying themselves or by evolving beyond this universe?
Yeah. And the other thing that comes back for me all the time is you talked about, let's just go visit, what was it, Pluto? If we do it at the right time, it'll only take 10 years of flight time. If we do it the wrong time, it'll take 50 years of flight time.
Or never.
And that's just within the solar system. Space is so big that I think it breaks our conception. Like, oh yeah, there's a billion of them over there, but they happen to be so far away that it's inconceivably far. The thought of going there doesn't make sense. Like generations won't, how many generations do you need to get there?
But let me throw you a wrench into those numbers for you. We use chemical rockets right now which burn very brightly, very briefly. There are better rocket engines. And not that I know that we have the answer to this, but we have a few good ideas about better engines, nuclear engines being one example of it. But imagine at the right period, right? This is certain moments where it makes sense to fly between the Earth and Mars. So I picked the right moment to fly between Earth and Mars, but I have a very special spacecraft. I have a spacecraft that can accelerate at exactly 1G. Okay? So it's like normal Earth gravity. The engine runs continuously. So I'm going to burn continuously at 1G of acceleration towards Mars till we get about halfway. Then I'm going to turn around and I'm going to burn at 1G to decelerate so that we arrive at Mars. How long did it take me to go from the Earth to Mars at 1G of continuous acceleration and deceleration?
1G.
Yeah.
How long does it take now? 18 months?
Yeah, 4 to 6 months, depending on a bunch of factors. I don't need you to do the math, friend. I'll just tell you.
I think I'm going to say 1 month.
It's 3 days.
Oh, okay.
So this is and so you can imagine if we could send 2 Gs, it'll be a day and a half. Given we can put smart people in space and create incentives to actually fly between bodies on a routine basis, we can make better engines. We can make the solar system far more approachable. We have not needed to. Every engine we've ever flown in space, we built on Earth. And first it had to survive being put into orbit and then operated. When we start building vehicles in space for space, they will be very different. And they will have new capabilities. We will learn to do things with the different resources we have available to you. We build spacecraft out of aluminum because we have to lift them into orbit. It makes no sense to do that once you're in
the weakest
space.
Metal that melts really easily.
Yeah, it has a whole ton of problems. And it's not that common. You know what would be easier to find? Nickel iron. They make asteroids out of this stuff. You know, maybe a true spacecraft built in space will be made from a nickel iron hull. It'll be heavier, but it won't matter. You know, we are not there yet. We're starting to get the ingredients to start thinking in terms of more powerful engines and vehicles built for interplanetary flight. We can do much better. We just haven't needed to yet. We will, but we're not there yet.
Well, I think we probably will. You're right. I mean, 400 years ago, we used wind and sails on the water. Yeah,
and still we coveted rare kinds of woods, like ironwood from the Indies, you know, for mass. Like one of the claims to fame for the Americans was their American oak made incredible hulls that we came up with a technique that they built the Constitution with, old iron sides. Well, there's no iron on the old iron sides. It's wood. Like there is abilities as you start functioning in that space to get better at it. We've just never done it because we have not had people building in space yet. The moment we do, things will happen.
Yeah. Well, that sounds very exciting. It's been really fun to explore this whole idea of, life in the universe. Where is it? Where could it be? And beyond. So, yeah, Richard, thanks for coming back on the show.
Well, my pleasure, friend. I will do this with you anytime you like. It's an excuse for me to sit down and update all that research, right? To say, okay, all the notes I've taken over the past couple of years since the last time we sort of dug into this, what have we learned? And I come out of it always excited. Like, I can't believe how much we've learned in this short amount of time.
If you just stop and take in everything that's going on, it's such an exciting time.
It is. Yeah. The civilization is doing amazing things right now. We have non-trivial challenges, and we could have spoken for an hour on coronavirus. I don't let anybody want to listen to it, but we could have, because again, we are doing remarkable things there as well. Some less remarkable also. But it's never been a finer time to be alive. It doesn't feel like it at times, but truly, we're at the height of our civilization right now.
I agree. I think there's some rough times, but I think there are bumps in the road.
Well, and so much more to do. Like, if you thought we've done everything, we're good. No, there's more to do.
Not even close. All right. Well, thanks so much for being on the show. It's great to chat with you as always.
You bet, brother. Thank you.
Yeah. Bye. This has been another episode of Talk Python to Me. Our guest on this episode was Richard Campbell, and it's been brought to you by Brilliant.org and us over at Talk Python Training. Brilliant.org encourages you to level up your analytical skills and knowledge. Visit talkpython.fm/brilliant and get Brilliant Premium to learn something new every day. Want to level up your Python? If you're just getting started, try my Python Jumpstart by Building 10 Apps course. Or if you're looking for something more advanced, check out our new async course that digs into all the different types of async programming you can do in Python. And of course, if you're interested in more than one of these, be sure to check out our Everything Bundle. It's like a subscription that never expires. Be sure to subscribe to the show. Open your favorite podcatcher and search for Python. We should be right at the top. You can also find the iTunes feed at /iTunes, the Google Play feed at /play, in the direct RSS feed at /RSS on talkpython.fm. This is your host, Michael Kennedy. Thanks so much for listening. I really appreciate it. Now get out there and write some Python code.